Welcome to part 2 of our discussion on introductory chemistry topics. This is part 2 of Intro Chem for my microbiology course for my college students that I have in that course. And so let's begin with important biological molecules. So looking at two terms here, organic and inorganic. Organic compounds always contain carbon and hydrogen, both of them together, always carbon, and typically we only think of it just containing carbon alone, but hydrogen also present as well in organic compounds. And so those two elements become the backbone on which all organic compounds are built. Inorganic compounds typically lack carbon, and so they are free of carbon, and so we classify them as inorganic. So we'll be looking at mainly the organic compounds and the four major organic compounds that make up all living things. So before we get into that, let's look at some inorganic compounds, beginning with water. And remember these terms that I use for covalent bonding, polar and nonpolar. So a polar molecule is any molecule that has an uneven distribution of charges. So as I described in part 1 of this lecture series, there is a partially negative charge on the oxygen atom because it's pulling hydrogen's electrons closer to itself because it has 8 protons compared to hydrogen's single proton. And so as a result of that, oxygen has a partially negative and the hydrogens have a partially positive charge. Nonpolar molecules, they have neither positive nor negative ends. And so we say it's nonpolar, so there's no regions of charge on a nonpolar molecule. And then this little phrase here, like dissolves like. What that refers to is polar molecules will dissolve other polar molecules, and nonpolar can dissolve other nonpolar molecules. So, for example, if you were to get, think of Sharpie ink. Sharpie ink is a polar or nonpolar? Well, for one thing, it's going to be a kind of a complex compound of inks combined together to make these markers. But overall, and you ask yourself the question, well, does Sharpie ink, does it dissolve with water? Well, no, it doesn't. And so therefore, Sharpie ink must be nonpolar, or have a majority of the compounds that make it are nonpolar compounds. So how do you get Sharpie ink out of your clothing, say, for example? Use another nonpolar compound like alcohol or acetone, which doesn't dissolve it very well, but it kind of dilutes it, diffuses it out through. It's maybe not as dark as it was before you used the alcohol or the acetone. So typically nonpolars do not dissolve other nonpolars very well. In some cases they do a very good job at it, like for example with paint thinners, mineral spirits. Those are all nonpolar compounds that can break down and thin out paint, and basically it's dissolving the paint molecules. We call it paint thinner, but it's actually, we could say, a paint dissolver. The paint thinner is moving in between the molecules of paint and separating them out. And so that's a nonpolar, kind of separating or dissolving another nonpolar compound. For polar compounds to dissolve, so you could dissolve, say, sugar or salt in water, and sugar or salt have charged areas on them, and so water is able to dissolve those substances. So like dissolves like. It's a general rule of thumb, just help you classify these as polar molecules dissolving other polar molecules and nonpolar dissolving other nonpolars. So 3 terms related to this with things dissolving: solvent, solutes, and solutions. And notice all these terms begin with the same prefix, and they're all referring to a kind of a watery, liquidy solution. Like, for example, the watery portion of a cell is called the cytosol within the cytoplasm. Cytoplasm is everything in between the cell membrane and the nucleus. The cytosol would be the watery portion of the cytoplasm. So SOL is referring to a liquid or of some type. So a solvent is the substance that does the dissolving, and the solute is the substance that is dissolved, and then the combination of the two together is called a solution. So you have a sodium chloride crystal in this example, and you can dissolve it in water, where the negative regions of the water molecules, the oxygens, are attracted to the positive sodium ions. And on the other end, on the other side of the coin, we have the chloride ions are being dissolved in water by the positively charged hydrogen atoms. And so the sodium chloride crystal dissociates or dissolves in water. And the water molecules are doing this because they have regions of charge. And so they're searching out other regions of charge in the solute, and then they can separate them out. Now, let's say you try to, you want to dissolve, say, vegetable oil in water. It's not going to work because the vegetable oil is a nonpolar substance. It has no regions of charge. And so there's nowhere for the oxygens or the hydrogens of water to attach themselves to or to be attracted to. And so the vegetable oil cannot become dissolved in water as a result of that. So there's no regions of charge, and so the water molecules can't take the vegetable oil molecules apart, basically, is what's going on. Now, with water, I mentioned before about the hydrogen bonding, and we looked at that earlier. Hydrogen bonding makes water molecules, it makes the water an excellent temperature buffer. So these hydrogen bonds can absorb a lot of energy before that energy is great enough that it can actually break those bonds. So in order to do that, it has to reach a temperature that's relatively high for a molecule that is so simple and has these chemical properties of 100 degrees Celsius or 212 degrees Fahrenheit at sea level. So this hydrogen bond is an excellent, it makes water an excellent temperature buffer. So it can absorb a lot of heat energy, which is very important for cells because the chemical reactions, many of them that are happening within in a cell, are catabolic and they're releasing energy. They're exergonic reactions. And so that energy can be absorbed by the hydrogen bond in the water molecules that make up, on average, about 70% of our cells. And so our cells can absorb all this, are able to carry out all of these biochemical processes because water is in abundance in the cells, absorbing this heat energy and preventing it from creating other problems within the cell, like heating up too much and denaturing enzymes. So this works well within living systems, and it also works well out in the environment as well. And it, of course, regulates the climate and the temperature of the Earth on a large scale when we think about all the water that we have on this planet. And so you can look at it at a microscopic scale within a cell, but you can look at it macroscopically as well on the entire Earth and how water is functioning as a temperature buffer on both of those scales, from the very microscopic to the very macroscopic. Acids, bases, and salts. So an acid is a substance that dissociates or dissolves into one or more hydronium ions. That's what the H plus is. So for example, hydrochloric acid, when put in water, it will dissolve into hydronium ions and chloride ions. And if a substance does break down and release hydronium ions or increase the hydronium ion concentration, we call that an acid. On the other hand, a base is a substance that dissociates into one or more what are called hydroxide ions or negatively charged ions. So the example of sodium hydroxide, put it in water, it'll break down into sodium ions and hydroxide ions. And so that's what we call a base. A salt is a substance that dissociates into cations and anions, neither of which is the hydronium, the positively charged ion, or an OH negative. So for example, NaCl, which we call salt, it's called a salt because, or I should say this, it's called salt because it is a salt. It's dissolved into charged particles into ions, neither of which is H plus or OH negative. So you have sodium chloride and potassium chloride and calcium chloride. Those are all salts because when they're put in water, they will dissociate into charged particles, neither of which is hydronium or hydroxide. Now, looking at acid-base balance within a system, a biological system, we'll say, for example, since this is microbiology within a cell, there is a balance that needs to be created, or homeostasis. So there's a homeostatic mechanisms that are in place within living things so that this acid-base balance is kept and maintained. So the amount of H plus ions in a solution is expressed as pH. And pH stands for the potential of hydrogen. So the P is always lowercase and the H is always capital because the H is referring to hydrogen. It's the chemical symbol for hydrogen. Increasing hydronium ion concentration, and that's what the brackets mean around the H plus, that means concentration. So you increase the concentration of that, you're increasing the acidity of the solution, and if you increase the hydroxide ion concentration, that increases alkalinity. And in the realm of living things, we're looking at a pH of about 6.5 to 8.5. That's typically where most living things like to dwell. Now, of course, there are outliers. Some of them love to be in a pH of 1 or 2. Those would be acidophilic organisms. And some of them like more basic pH as well on the opposite end. But typically, most life and most forms of life typically like to reside within that pH. Now, why is that? And this is so often the case with many of these factors like temperature or pH. It's because of enzymes. These are the pH ranges in which enzymes can function optimally. And anywhere outside of that pH, they won't work nearly as well, or if you get too far away from a particular acid, a pH balance, it can denature the enzyme and make them totally non-functional. So we measure this hydronium ion concentration on a scale called the pH scale. And you have learned about this before, where you have anything that's less than 7 is acidic, and anything greater than 7 is basic. And 7 is considered to be the neutral pH. What makes it neutral? Well, if you look at the graphic in the middle there, the hydronium ion concentration equals the hydroxide ion concentration. So to say that saying something is neutral, you're not saying that there are no ions. There are definitely ions, but there's a perfect balance between the positively charged ions and the negatively charged ions. And then once you get away from that equality, you're either getting more basic or you're getting more acidic, depending on which ion is increasing. And then my micro students, you can click on that video link. It's a good TED Ed video that simply explains acids and bases and how acids and bases form by either donating protons or taking away protons. And if a substance donates protons very easily, we say that it's a strong acid. And if it takes away protons very easily, we say that it's a strong base. As a result of that. And this video explains it nicely. So we'll begin looking at organic compounds, and we'll start with carbon, because that's the basis of all organic compounds and what makes them and creates their chains and their skeletons. So the chain of carbon atoms of an organic molecule, that's called the carbon skeleton. Whether it's just one carbon, that's not really a chain, like for example in methanol, or if you have 2 or 3 or hundreds of carbons linked together. And the functional groups are the groups within a compound that are responsible for most of the chemical properties of that compound. So in this case, the OH, that's highlighted there in the purple, those are all the functional groups. And it so happens that you'll notice that all of these compounds end in OL. Well, that OH functional group makes these compounds alcohols. And so you know that methanol and ethanol and isopropanol are alcohols, number one, because they end in OL, so they have the suffix OL, and that's what chemists decided to do, so that if it's an alcohol, we're going to end it with an OL. But also, if you looked at the structural formulas of these compounds, you would see that there's an OH group, and that's the functional group. And functional groups are different between these organic compounds. This one I just picked because it was simple, pretty easy to determine that and see it. Small organic molecules can combine into larger, what are called macromolecules. And as you know, macro means large molecules. Macromolecules are polymers consisting of many small repeating molecules. And so these Small repeating molecules are called, or the small molecules that can become repeating, they're called monomers. So these two terms, polymer and monomer, are two very generic terms. Poly means many, and mer refers to part. So polymer means many parts. Mono is a prefix that means one. So one part. So you have these monomers that are single units that can join together through chemical bonds and make these long chains of compounds that are called polymers. So there isn't a specific compound called a monomer. There's not a specific compound called a polymer. These are just generic terms that are used for that. So how are these compounds made? Well, there are two ways that there's a way to make them or build them, and there's a way to break them apart. Monomers join together by what are called dehydration synthesis reactions. These are anabolic reactions. And you'll notice the term dehydration. So water leaves these molecules. So a molecule of water is released in these reactions. So these are anabolic or building up reactions in which water is released. Now, polymers, the larger molecules that are joined together, they can be separated by hydrolysis. And these are catabolic reactions. And in this case, a molecule of water is absorbed in these reactions. And so, as a result of that, this molecule then breaks apart. And if you look at the term hydrolysis, maybe if you pronounce it hydrolysis, hydro refers to water, and lysis means to split. So using water to split the polymer into monomers or into its smaller parts. So dehydration synthesis builds, hydrolysis breaks. And you can see that in the example here on the bottom where glucose can join with fructose, a molecule of water leaves, and it makes sucrose. Or you could go in the reverse where you have sucrose, add water, and it splits it into glucose and fructose. So we have these are reversible reactions, and these conditions are needed, either removing water to build or adding water to break. So we'll look at the macromolecules, and there are 4 of them. And the first one that we'll look at are carbohydrates. The other ones are lipids and proteins and nucleic acids. So carbohydrates, if you look at the term carbohydrate, they're made of carbon, hydrogen, and oxygen. So the prefix carb refers, of course, to carbon, and then HYD is referring to hydrogen, and then ATE, if the suffix AT is on the end, that means there's oxygen present. So carbs are important for structure and to be used as energy sources within cells, and they consist of just 3 elements, carbon, hydrogen, and oxygen, often in the ratio of 1 to 2 to 1. And it doesn't have to be exactly 1 to 2 to 1. Like in the case of glucose, it is exactly 1 to 2 to 1. You have 6 carbons, 12 hydrogens, and 6 oxygens, and that reduced ratio is 1 to 2 to 1. Amylose is a large carbohydrate. It's a repeating unit of glucose. So in this case, glucose becomes the monomer that's being joined together to build up polymers. And in this case, we have the carbohydrate amylose. Now, there's different categories of carbohydrates depending on how many parts or units there are. There are monosaccharides. Mono means one. So these are single unit simple sugars with 3 to 7 carbon atoms like fructose, glucose, and galactose. So they're single entities, and so we would call them the monomers. Disaccharides, di means 2, and so now we have 2 monosaccharides joined together via dehydration synthesis. And of course, disaccharides can be broken down into monosaccharides by hydrolysis. And then other types of carbohydrates, we have oligosaccharides. The prefix olig means not many. So oligosaccharides consist of 2 to 20 monosaccharides. Poly means many. So polysaccharides consist of tens or hundreds of monosaccharides joined together in repeating units, one glucose molecule after the next, joined together through the process of dehydration synthesis. Some examples of polysaccharides are starch, glycogen, dextran, which forms a polysaccharide that forms dental decay and bacteria can grow in on our teeth, Cellulose within plants, those are all polymers of glucose that are covalently bonded together in different ways. So they could be straight linear chains, or sometimes they're branching. Chitin, which is found in the exoskeleton of insects like this Goliath beetle on the left, or in Mr. Crab, he's got chitin in his exoskeleton. They're made of two sugars repeating many times over and over again. So these carbs can be joined together in a variety of different ways. So what I want my students to remember are, and this is for all four of these macromolecules, are the monomers, what are the building blocks, and the polymers. So with carbohydrates, the monomers are monosaccharides, and the polymers are polysaccharides, or starches. So the basic building blocks are the monosaccharides, and the larger units that are built from those basic building blocks are called polysaccharides. Okay, I'm going to stop there for part 2. There's going to be a third part coming up where I'll finish out talking about the macromolecules and a few other things to wrap things up in this chapter. So I hope this was useful for you and maybe even enjoyable. And please stay tuned for part 3, and thanks for watching.